Assalamualaikum and a very good day to my lecturer, Professor Madya IR, Dr. Iza Sazanita, and everyone watching. My name is Fathi Nanjuri bin Yuhi. Today I will be presenting my work for the ETS551 Digital Signal Processing assignment. In this presentation, we will dive into two distinct filter design assignments. First, a finite impulse response or FIR filter tailored for low-power biomedical monitoring. Second, an infinite impulse response or IIR Butterworth filter engineered for power quality systems. Let's jump right into the first design. For assignment 1, we are tasked with designing a causal FIR low-pass filter for a battery-powered portable biomedical device. Because this device runs on a battery, our design philosophy cannot just focus on technical performance. We have to balance the whole life cost, which means explicitly optimizing energy consumption, memory footprint, and computational load. Our given system parameters require a passband up to 1 kHz, a transition width of 0.5 kHz, a minimum stop band attenuation of 45 decibels, and an operating sampling rate of 5 kHz. Before looking at the math, let's analyze the overall magnitude response shown here in Figure 1. The dashed line represents the ideal brick wall low-pass filter. As we know, an ideal filter requires an infinite impulse response, making it physically impossible to realize in a causal system. By applying a Hanning window, our actual response, represented by the solid blue line, smoothly rolls off across the shaded 1 to 1.5 kHz transition band. The band remains remarkably flat, within 0.05 decibels of unity gain, while our stop band provides a worst-case peak attenuation of roughly negative 43.9 decibels. Let's walk through the manual windowing design steps. First, we normalize our transition width by dividing it by the sampling frequency, yielding a value of 0.1. Next, using the standard Hanning window parameters, where the normalized transition width equals 3.1 over n, we solve for the filter order n, getting 31. However, to preserve linear phase characteristics and create a symmetric type I filter, our order n must be an even integer. Therefore, we round 31 up to n equals 32, setting our center of symmetry alpha exactly at 16. This places our cutoff frequency Fc at 1250 Hz, which corresponds to a normalized digital frequency of exactly pi over 2 radians per sample. To calculate the actual windowed coefficients, we multiply our ideal impulse response, HDN, by the Hanning window function, Wn. Here is where an interesting mathematical simplification happens. Because our cutoff frequency, omega c, is exactly equal to pi over 2, the term sin, omega cm, inside our ideal impulse response evaluates to 0 whenever m is a non-zero even integer. Consequently, every single even index coefficient drops to exactly 0. Combined with the linear phase symmetry around the center tab at n equals 16, our complex manual calculations reduces to solving only a handful of odd coefficients. To justify why n equals 32 is truly optimal, let's look at the whole life cost analysis, where we compare orders 32, 33, and 34. By leveraging structural symmetry, a smart hardware implementation only performs one multiplication per coefficient pair. Thus, the multiply accumulate, or MAC, count per sample is roughly half the total tap count. Notice that bumping our order up to n equals 33 achieves absolutely nothing. It requires identical MACs, uses an extra memory word, and introduces a non-integer group delay of 16.5 samples, which disrupts sample synchronization. Moving to n equals 34 is even worse. It hikes our computational burden to 90,000 MACs per second, a 5.9% increase over n equals 32. On a wearable medical device, that extra 5.9% processing overhead translates directly to unnecessary battery drain over months of operation. Thus, n equals 32 is our clear winner. Now let's switch gears to assessment 2, a digital Butterworth low-pass IIR filter designed for a power quality monitoring system. In this environment, our priority is effectively suppressing steady-state power line interference while perfectly preserving transient events like voltage sags, swells, and harmonics. Our design framework dictates a passband ripple under 27 decibels, a minimum stopband attenuation of 40 decibels, with normalized digital edge frequencies set to 0.3 pi and 0.5 pi. Because we are mapping our filter from the analog domain to the digital domain via the bilinear transform, we must pre-warp our digital edge frequencies using the tangent convention. This yields an analog prototype passband frequency omega p of 0.5095 and a stopband frequency omega s of exactly 1. Using these values to calculate our selectivity factor K and discrimination factor D, the mathematical formula for our filter order yields approximately 2.22. Since filter orders must be integers, we round up, establishing a third order filter, n equals 3. Rounding our order up from 2.22 to 3 means our design constraints no longer cross at a single point. Instead, they give us a flexible operating range for our 3 decibel cutoff frequency between 0.1808 and 0.2154. We select a clean, convenient value of omega c equals 0.2. Looking at the pole zero map in figure 2, a third-order Butterworth filter generates 6 poles distributed evenly across an analytic circle. To guarantee a stable and causal system, we discard the 3 right-half plane poles and strictly retain the 3 left-half plane poles P1, P2, and P3. Multiply out our stable poles give us our continuous time analog transfer function HS, shown here, which maintains a perfect unity DC gain of 1. Next, we apply the bilinear transform substitutions to map our analog system into the digital Z domain. This yields our final digital transfer function, Hz. Take a close look at the numerator coefficients. 0.0054, 0.0161 z power negative 1, 0.0161 z power negative 2, and 0.0054 z negative 3. They map perfectly to a symmetric 1:3:1 ratio, which is the Class A binomial signature of a robust Butterworth low-pass design. To verify our design accuracy, we ran a validation script in MATLAB using the Butter, aka Butterworth filter order, and Butter routines. MATLAB independently confirmed an order of n equals 3, matching our manual calculation perfectly. Evaluating our digital transfer function at the critical operational boundaries confirms total compliance. At our passband edge of 0.3 pi, the magnitude attenuation is negative 24.39 decibels, passing our constraint with a comfortable 2.6 decibel margin. At our stopband edge of 0.5 pi, the attenuation hits negative 41.94 decibels, comfortably beating the negative 14 decibel requirements. Both constraints are met successfully with clear margins. In conclusion, both digital filters have been manually designed, optimized for their target real-world operating environments, and rigorously cross-checked for absolute mathematical accuracy. The FIR design balances computational economy for wearable medical applications, while the Butterworth IIR filter delivers sharp, reliable performance for power monitoring grids. This concludes my presentation. Thank you very much for your time.